Okay, in this video, we're going to talk about strong, weak titrations. It's really important you understand strong titrations, which we covered in the previous video. Because today, the titrations are going to be more complicated and the problems more difficult. So let's just briefly review what we talked about in the previous video about strong base, strong acid titrations. So you'll have something down here that's a strong acid like maybe HCl, and you're titrating it by dropping slowly, drop by drop, a strong base like sodium hydroxide into this beaker of hydrochloric acid, whose molarity you may or may not know. The titrant, sodium hydroxide here, is maybe 2 molar or something, a known concentration, and you're slowly adding certain volumes until you reach the equivalence point, which is really the goal. Okay, now at the beginning, before you drop anything in, there's just H plus and Cl floating around down here. And so it's very acidic, right? The pH at the beginning, if I'm thinking about making a graph here of the pH on the y-axis versus the volume of NaOH I'm adding, at the very beginning, my pH is something like 1. Very acidic because I haven't added any base yet. But then once I start to add OH minus, I'm canceling out some of the H pluses in there, and I will move to the right on this graph as I add more and more volume, the pH will go up. Now, eventually I add enough NaOH that I'm canceling out the last bits of H plus down here, right? So there's lots of H pluses floating around. Eventually, I'm getting to the equivalence point, right? The equivalence point being that point where the moles of acid equal the moles of base. And so at the equivalence point, I've exactly canceled out with my OH minuses or neutralized all the H pluses so that all that's left down here is chlorine minus, which is not a base, doesn't affect the pH, and water, which is perfectly neutral at 7. So at the equivalence point, I will have a pH of 7. And that corresponds to some volume down here of NaOH I've added. And so the curve of how the pH changes gets exponential around that equivalence point and then sort of levels back off. Right? So after the equivalence point, now you've added too much OH minus, and now in addition to some chlorine and water, which is just neutral overall, you've added too much, and now there'll be OH minus floating around down here. And so your pH will be very basic. Okay, and you'll end somewhere at like 11 or 12 or 10 pH, a basic pH. All right, so that's strong acid, strong base titration. Once we switch this to a weak acid titration instead of a strong acid titration, the situation is going to be a little bit different. Okay, so maybe consider here a titration where we're using CH3COOH. Okay, sort of a prototypical weak acid, and we're titrating it still with a strong base like NaOH. Okay, if the acid is not one of the strong acids we learned about in previous videos, then it's a weak acid. Okay, so this is not one of the strong acids, it must be a weak acid, and we're titrating it with a strong base. If I'm thinking about what this titration curve would look like, well, it's a weaker acid, so the pH is going to start out, even before I've added any OH, at something higher, maybe 2, 2.5, 3. It's not going to be a strong acid with a pH of 1, right? And actually, it's probably better to exaggerate this a little bit and say, maybe the pH is starting around 4 or something, 3.5, we'll say. Okay, that's our starting pH. As I add OH minus, I'm still going to be canceling out some of that weak acid. I'll still get this sort of exponential growth near the equivalence point. And then I'll get this sort of leveling off after that. This is really a poor drawing, so you're welcome. This equivalence point, let me actually fix this. This equivalence point is actually going to be much greater than 7. I shouldn't say much. It's going to be greater than 7. Okay, maybe something like 8. Okay, so the first difference here is that our starting pH is going to be higher because the acid is less strong. It's a weak acid. The second is that there's going to be a smaller total change in pH, which is, one factor just being we're starting at a higher pH, so of course it's going to be a smaller total pH. But the change around the equivalence point is still going to be this exponential kind of growth, but it's probably going to be somewhat smaller of a growth than this very quick exponential change we had here. And that's in part due to starting at a higher pH, but also this buffering region tends to be larger in a weak acid, strong base situation. But the last point I want to make here is the most important. The pH at the equivalence point is going to be larger than 7 for this weak acid, strong base titration. And to understand why that is, let's come back to my strong acid, strong base situation. When I'm at the equivalence point, I've added precisely enough OH minus to cancel out all the H pluses. And so if this is sodium hydroxide and hydrochloric acid, the only stuff floating around down here is Na plus and Cl minus, which are just spectator ions and don't affect pH at all, and water, which is completely neutral, hence the equivalence point being 7. But once I change this to a weak acid, it is not Cl minus that's floating around down here, but it is, in this example at least, the conjugate base of this acid, which will act like a base and affect the pH. So the conjugate base that would be floating around down here is CH3COO minus. Yes, you've neutralized the H plus off of that, but you've left behind this CH3COO minus, which is a base and will affect the pH. And so at equivalence, you've gotten rid of all the H pluses, but there's still something left behind that is basic. Hence, the pH at equivalence will be basic, not exactly neutral. Okay, so let's get into this a bit more and think about the types of problems we might have to solve and our strategy for solving them. So here's a more elegantly drawn titration curve. For a weak acid down here, you can just call it HA, right? Maybe this is hydrofluoric acid, HF. Maybe this is the previous example, CH3COOH, right? But not one of the strong acids. And so at the beginning, our pH is something like 2.5, right? Only weak acid is present down here and water. So there's HA. We haven't started titrating yet. And so if you're asked for the pH before the titration even begins, well, you can't just do negative log of the molarity like you could back here. For a strong acid, strong base, before the titration, we just say, okay, it's negative log of whatever that HCl concentration is. It's a strong acid. That's the pH. Not the case here. Remember, you have to, for a weak acid, get the Ka involved, do an ice chart. You'll wind up with like x squared. This equals the Ka, solve for x, negative log of x, all of that to determine the initial pH before the titration even begins. Of course, the second type of problem is, okay, now you've added some titrant. Well, some of that acid is going to be neutralized by OH minus, and you'll have some HA remaining, but you'll also have created some conjugate base. And so you'll have this buffer region, just like you did in strong acid, strong base. So this second type of problem you'll be asked for weak acid, strong base is quite similar to strong acid, strong base, where you just use the Henderson-Hasselbalch ice chart, then Henderson-Hasselbalch. Before the titration begins, this is totally different. You're using Ka instead of just doing negative log of acid concentration. At the equivalence point, this is going to be much different than our strong acid, strong base. We will do an ice chart, figure out what the volume is, what the new acid and base concentrations are, and then do a second ice chart. Oh no. Okay, so this will be much different than our strong acid, strong base titrations. Lastly, so these are the 4 different types of problems we might be asked about to calculate pH for 4 different regions before the titration starts, before the equivalence point, at the equivalence point, and after the equivalence point. Okay, and you can see here the pH at the equivalence point is 8. Instead of 7, it's moved up. After the equivalence point, how do we determine the pH? This is going to be pretty similar to what we did for strong acid, strong base. We've added too much base. We'll do an ice chart, figure out how much strong base is floating around, calculate the concentration based on the new volume, do negative log to get pOH, and we can get pH from there. Right, so after the equivalence point, you've completely neutralized the acid. There's just going to be OH minus floating around. And actually, there'll also be conjugate base, A minus, but it's a weak conjugate base and won't really affect the pH nearly as much as the strong base does. So we really only have to worry about the OH minus after the equivalence point, not the conjugate base. We do have to worry about the conjugate base at the equivalence point, where it's the only base floating around. Okay, so let's update our strategy here with how to calculate the pH of a titration problem. We had 6 steps when it was strong acid, strong base. We're still going to start the same way with a titration problem and calculating the moles of acid and moles of base, assuming we've begun the titration. Remember, if the titration hasn't started yet, then it's just a Ka problem for weak acids, which I'll talk about on the next slide. But assuming we're before equivalence, at equivalence, or after equivalence, we're going to be calculating first the moles of acid and moles of base. We're going to write a reaction and do an ice chart. And then we're going to stop to consider where we're at. If we're before equivalence, we use Henderson-Hasselbalch. Okay. If we're at equivalence, meaning the moles of acid equals the moles of base, okay, then we're going to go through and determine, okay, what is the new volume? What are the concentrations of any acids or bases that are left? And then if we're at the equivalence point, we might have to do a second ice chart. So let's look at this in action. And let's just hypothesize we're titrating CH3COOH with NaOH. Okay, and so again, when it's written like this, we're titrating this acid with a base. That means the acid is the thing floating around down here. And we're titrating it with, that means the sodium hydroxide is up here in our burette. We're titrating this weak acid with this strong base. So before the titration even begins, let's think about the reaction that is happening. Okay, always good to sort of draw a picture, say, okay, we're not adding anything left yet. So what is happening down here to this CH3COOH? Forgot a carbon there. There we go. So if I haven't added any hydroxide yet, the titration hasn't begun. Well, this is just a weak acid sitting down there. But a weak acid doesn't stay as a weak acid. It makes an equilibrium where some of that acidic proton pops off of the weak acid to generate its conjugate base. Okay, so this is the reaction that's taking place just with the weak base sitting here in the beaker. And so I have to consider an ice chart based on this. Okay, so I'm not adding any titrant yet. This is just worrying about what the pH is of this weak acid. And we did a bunch of problems, and there's a whole lecture video of pH of a weak acid. That's all this is. This is a problem we've already done, just in the new context of it being before a titration starts. It's just a weak acid sitting there. What is the pH? You did plenty of things like this. You know, if this was 0.2 molar weak acid, well, okay, it's starting at 0.2 molar. It's 0 on the right. This is going to go up by some amount X. The weak acid's going to have dissociated by some amount X. Right, so I'll then have Ka is products over reactants. And I'm going fast through this because we've done tons of problems like this in past videos. This is just pH of a weak acid. So go back and watch that video if you need help on this first part of titration problem, which is really just a pH of a weak acid problem. Okay, and remember, you can use this like neglect X rule. if it's less than 5%, right, to simplify and avoid the quadratic formula. Whatever concentration you get here at the end is my H plus concentration, so negative log of that is the pH. Okay. And that pH will be higher than if it was a strong acid, right? Where the pH will be something more like 1. Well, here we're starting, the pH is going to be something like 3.5, right? So here's where we are on the curve before this has even started. Okay, so that's the first type of titration problem you might be asked for weak acid, strong base before the titration even begins. The second type will be, okay, we've started the titration. We've dropped in some OH minus, but it's before the equivalence point. Okay, so draw a picture. We've dropped some OH minus in here. Remember, I'm just sort of neglecting the sodium plus here and just thinking about this as OH minus. Okay, let's think about the reaction that's happening. Well, I have the weak acid down there, but now I'm not letting it fall apart. I am reacting it with OH minus. This is an acid base, so those will neutralize to make water, plus the conjugate base. Okay, and sometimes students have confusion about how do I come up with like the formula of this other thing on the right side? Well, remember, what does a base do? It neutralizes one of the hydrogens in the acid. H plus OH makes H2O. So the other thing here is going to be, right, the remainder of this acid you started with. Okay, this is going to be the conjugate base here, which you'll remember we get by just removing a proton from the weak acid we're starting with, or the acid we're starting with. All right, so your reaction here, once the titration has started for weak strong, is always going to look the same. It's the weak acid plus OH minus making water and the conjugate base of the weak acid you started with. Okay, that's how it's going to look. Now, here you're going to calculate moles because now a volume is changing. Remember, in our ice charts for titrations, once the titration's begun, we're going to be using moles for our starting amounts of acid and base. And there's going to be no water, we don't have to consider that. There's going to be no conjugate base to begin with, okay? Even if there was tiny amounts, I guess we're neglecting it. Okay, so up here, we're free to use concentrations because we haven't started the titration, the volume's not changing. All right, so our concentration of that weak acid just goes in there. But once we start pouring two things together, open up our burette and add some OH minus in here, well, now the volume's changing, and if we write a reaction and are doing an ice chart, we better be putting moles in there. So calculate moles of acid, calculate moles of base, right? Write a ice chart. But since we're before the equivalence point, the OH minus will be the thing that gets used up and goes to 0. There'll still be some weak acid left. You'll have created some conjugate base, and then you'll use Henderson-Hasselbalch based on these two amounts of base and acid down here. And we'll do an example problem on the next slide. All right, I just want to show you the format of how you're problem solving each of these 4 different regions. Before titration, problem number 1. Once the titration started but before equivalence, problem number 2. Problem number 3, what if we're at the equivalence point? Okay, so this is the third type of problem you might encounter for a weak acid, weak base, or weak acid, strong base kind of titration. Okay, at the equivalence point, it's important to remember whenever you read equivalence point, moles of acid equal moles of base. Because sometimes the problem may not give you enough information to like calculate moles of acid, calculate moles of base, but if you're told it's the equivalence point and you have the moles of acid, then you immediately know the moles of base. Those two are equal at the equivalence point. Okay, the pH is not going to be 7 here because there's going to be some conjugate base of the weak acid left over that is still basic. and will affect the pH. Okay, so if we're still considering this as our weak acid, and we're adding OH minus, we're still having the same sort of reaction happen. It's just now our ice chart is going to have the initial amounts of acid and base that are equal, such that they exactly cancel each other out. Right, so whatever moles we start here with OH, maybe in the problem it was 0.1 moles of OH, and it was equivalence point, so it's 0.1 moles of acid. Those two exactly neutralize, and so the right side goes up by that same amount, and my conjugate base in the end has 0.1 moles. So now I have a beaker of just 0.1 moles of this solution floating around. That's going to affect the pH. Okay. How do I predict what the pH will be? Well, now I need to do a second ice chart. Okay, so we have to think about this titration happening sort of in two phases. First, we add the OH, and it completely neutralizes the weak acid, generating conjugate base. And now let's think about a new situation in the beaker, right? Where now I've just created essentially a beaker of this conjugate base at some large volume because I've poured two things together. So I'm going to take this moles and divide it by the total volume given in the problem. Maybe it was 40 mils and 50 mils, or 50 mils and 50 mils, so it's 100 mils, or 0.1 liters. And so I'm going to take the moles of this conjugate base and turn it into a concentration of conjugate base. In this example, I guess it's 1 molar. And I'm going to make a second ice chart based on that. And I know this seems complicated, but the easy thing is that the second ice chart will always just be the reverse reaction of the first ice chart. So we've added base, it's neutralized the acid, I've generated this base, and what does this base do when it's floating around in water? Well, it steals a hydrogen to make its conjugate acid. So the easy part here is that the reaction for the second ice chart is just going to be the exact reverse reaction that happens. Okay, and now I'm considering this sort of second stage of the reaction where I'm starting with this 1 molar weak base that I've created after the neutralization of the titration. And now this is going to go down by some amount x. This is going to go up by some amount x. And I'm going to have x squared over 1 minus x, right? These numbers will be different. I'm just making up numbers. But also keep in mind here that this now equals the KB, since I'm working with a base here. In this second ice chart, I will now need the KB of that conjugate base. I will need to solve for x here. What does x represent? The OH minus concentration. This is already in molarities. This second ice chart is fine to use concentrations because the volume is no longer changing. And so I've solved for x. That's my concentration of OH. I can take negative log to get my POH. All right, so you can see the equivalence point here calculation is really pretty difficult. You have a lot to do here. Always going to be these two ice charts. The second is the reverse of the first ice chart. The first ice chart is in moles. After it's done, figure out your concentration based on the new volume, and then use that concentration at the start of your second ice chart. Okay, so you have to practice a lot of these to get comfortable with it. They just take time. That's the third type of problem you might be asked for in this weak, strong titration. The fourth is after you've added too much base. All right, and this is very similar to, maybe I'll just try to solve it. Well, I can squeeze it in over here. You've added too much base. So you're still going to have the same reaction at first that you're thinking about. but this one gets a little easier. You're going to calculate moles of acid and moles of base, and here you've added too much base, so you'll be starting with too much OH minus compared to the weak acid you began with. Okay, and so here the weak acid gets completely neutralized. Oh, sorry, and goes to 0. And there will be some strong base left over. It is true that you will also be creating some conjugate base over here, but I won't need to worry about that conjugate base and how it affects the pH, because a strong base, sodium hydroxide, that is left, is going to completely determine the pH. I don't have to worry about this weak base when I have a strong base. So all I do is take this moles of strong base that is left after equivalence point, and I've neutralized all the weak acid, divide it by the new volume. That gives me the OH concentration. Take the negative log, I get POH, convert it to pH. Okay, I know that's a lot. So let's do a practice problem to try to put this into some context. Okay, the first one I'm going to go through a little quick because I have a second one that is going to demonstrate all 4 places of the titration you might be asked to calculate. Okay, so feel free to pause the video here, at least try to identify what's the acid, what's the base, what's the reaction, and what type of titration problem is it? Before titration, before equivalence, at equivalence, or after equivalence? And if you're comfortable, go ahead and work it from there. Okay. So here I have 45 mils of NaOH. That's clearly a base. And 50 mils of CH3COOH. That's clearly the acid. This is an acid-base titration. And I have started the titration. I have added things together. So I know I'm not before equivalence point here, or before titration here even begins. I've started the titration. So I'm definitely going to need to write the reaction here of these two things being added together. And so my approach here will be the same to start, no matter if it's after equivalence, at equivalence, or before equivalence. As long as the titration has started, which it clearly has here, then I need to write a reaction, make a nice chart, and calculate moles of acid and moles of base for this weak acid, strong base titration. Okay, so moles of acid, 50 mils at 0.1. That means 0.1 times 0.05 liters. That's 0.005 moles of the acid. I can do the same for the OH minus and figure out it's 0.0045. And I'm not starting with any conjugate base to begin with. So we look at these two numbers. Whichever one is lower is going to get completely used up. There's less OH minus here than there is the weak acid, so I'm going to completely use up the OH minus. The acid will go down by that amount. So 0.005 minus 0.0045 will give me 0.0005 moles at equilibrium. And my conjugate base will go up by that 0.0045. Because when a base neutralizes the acid, it is creating that corresponding amount of conjugate base. Okay, so clearly here I'm before the equivalence point. I have not added enough base to completely neutralize the acid. And so the strategy here is I'm before the equivalence point. Use Henderson-Hasselbalch on what remains. This is just like we did for strong acid, strong base. We were left with a conjugate acid-base pair. So I need the pH is going to be the pKa, which is negative log of the Ka, plus log of base concentration over acid concentration for the conjugate acid-base pair. All right? this is my weak acid, and this is my conjugate base. So those are the two concentrations I want. And although I really should put these in concentration and consider the new volume that has been created, 95 mils or 0.095 liters, right? I can convert each of these moles into concentrations by dividing by this liters and then plugging them in. But because the liters are going to be the same, right? 0.0045 divided by 0.095 for my base concentration, and 0.0005 moles divided by 0.095 liters for my acid concentration. So this will go down here, and this will go in here. Okay, the 0.095s will actually end up canceling out. So it is a nice little hack here that you can just directly plug in the moles here instead of the concentrations, instead of worrying about the total volume and having to do that extra step here. But either way you're comfortable doing it is fine. You plug these numbers in, you should wind up with a pH here of this one for 5.70. Okay. So this is just a random practice problem to let you try to identify where am I in this titration and what the approach will be. In this final practice problem, I want you to calculate the pH at all 4 regions. Before the titration started, after it started but before equivalence, at the equivalence point, and then finally after the equivalence point. And I think because this video is already going pretty long, maybe I'll just stop the video here and I'll record another video where I solve this in detail, which will probably take 15 minutes or so. So if you're comfortable, I would stop here and try to work this out before watching the next video on solving this example weak acid, strong base titration problem. Okay, we'll also then get to indicators and polyprotic acids as well in the next video solving this problem. So I'll stop the video here. See you next time.